Good morning, students. Uh, I welcome you to the class of physics. In today's class, we'll discuss about the BCS theory. In the last class, we have gone through the what is the meaning of superconductivity and how this superconductivity are applied in our day-to-day activities and in different fields of the life. And also, we discuss about the different characteristic of the uh, superconductivity. What is a special character when compared with the normal conductor and semiconductor? So what is the basic difference between this between them? We have just gone through with a brief idea. We'll just move forward in today's class to the BCS theory. Now, in today's class, we'll discuss about the BCS theory, and also we try to discuss about high temperature superconductors, and also we'll just do some numericals or depending upon the critical internal critical magnetic field. So before starting today's class, we should have aware of the fact that superconductivity is nothing but it is the phenomena which is exhibited by the materials who, when they are cooled at a particular temperature, and that particular temperature is said to be a critical temperature. So if this materials such as the mercury, lead, and so on, there are few different materials which exhibit this particular property. And there exists a critical magnetic field also at that particular magnetic field, right? So they behave as the superconductors. Now, the special character which is shown by the superconductors are nothing but it is the expulsion of magnetic field. We just call that as Meissner effect. In the last class, we discussed about this Meissner effect, and also we have gone for a formulae related to critical magnetic field. So in this particular session, we'll discuss about, we just start today's topic with the uh, BCS theory. So now we are trying to understand what is actually the BCS theory. And what is this BCS theory? When I say that BCS theory, it is nothing but Bardeen Cooper Schaefer. So just call that as a BCS theory. And now we'll just start this, right? We'll just call this as a BCS theory. BCS theory. Now, this is what the name of the scientist. Superconductivity is a phenomena which is arise uh, due to the relationship or interaction between the electron and phonon, right? So the superconductivity is a phenomena which occurs. It occurs. It occurs due to. So what this BCS scientist told us that the superconductive phenomena is occurring due to the interaction of, it occurs due to the interaction of, due to the interaction of, interaction of, interaction of electron with a C, interaction of electron, a phonon. Now, this is what phonon we'll talk about. Phonon is nothing but the particle which is produced with respect to the heat, right? So, electron, phonon, electron interaction, electron, phonon interaction. Now, which is said to be a Cooper pair, right? These interaction of electron, phonon, and electron is said to be a Cooper pair, right? So now they can be termed as low temperature superconductivity. Now, if this is the case, right? If this interaction is taking place between electron phonon interaction at a particular temperature, and we just say that is called low temperature superconductivity. right? So BCS has explained us regarding the low temperature superconductivity. So here, what is actually Cooper pair? When I say that we just say that this electron phonon interaction. So what is this actually Cooper pair? So a pair of electron which is very far from each other, but they are interacting with the lattice vibration. So we just say that is called the electron phonon interaction, and also this pair is termed to be electron Cooper pair. So what is actually Cooper pair? So Cooper pair deals with the what you can say the two electrons which are interacting with respect to the lattice vibration. We just say that it's called Cooper pair. Now in the examination he will ask you what is actually the meaning of Cooper pair. So the Cooper pair here terms as when we just plot a what you can say a semantic diagram. When we just plot a semantic diagram, see this is what Cooper pair. So Cooper pair says that when the electron here, see the electron and electron is interacting. See, they want to interact. This electron are interacting with respect to the vibration of this lattice, right? We just call this as a phonon. This lattice, this is called lattice vibration, and we just say this lattice vibration. Due to this lattice vibration only, the electrons are interacting with each other. So we just tell this pair, this pair is termed to be as the Cooper pair. This is very important aspect that we need to understand, right? So for low temperature superconductivity. So low temperature superconductivity actually deals with the uh, electron phonon interaction, and these electron phonon interaction is due to the lattice vibration, and we just call this pair of electrons which are interacting with the vibration of the lattice just said to be a Cooper pair. Right now, this is what actually BCS has explained us. Now, when we just go a little bit, right, we just little bit move forward in this particular aspect here. The what is happening inside a solid, right? When we talk about a solid material, right? Let us just deal with this solid material. So, what is happening in this solid material? What is actually happening in solid material? An electron in a solid exert an attractive force to an adjacent ions, and with this what will happen is that there will disturb in the lattice, right? See, we just say that what is happening to the uh, electron, electron electron interaction, how this is taking into coming into existence. We just say that an electron in a solid exert an attractive force on the adjacent ions, and they disturb the lattice, and if the second one is interacting with the disturbed lattice, it experiences an attractive force at low temperature, and this attractive force is very much dominant with respect to the repulsive force, right? You are aware that like poles uh, repulse and unlike polar attracts. Here there are two like poles, electron is a negative charge, so the negative charge they try to repel out, right? And this repulsion is nothing but existence of the repulsive force. And again, when we just see that this electron are interacting with respect to the lattice vibration, and again, since here we'll just consider that there exists a smaller, what you can say, attractive force also, and these attractive force are resulting in what you can say dominating the repulsive force. Now we just say that this is the what is happening inside the solid when the when we just say metallic crystal, right? Let us consider the metallic crystal, in which you'll find that there will be definitely you'll find the electron interaction in the metal. When I talk about metal, it is a conductor, so there will be an interaction with the electron. So here this interaction is possible with respect to the phonon in certain materials, that is at some critical temperatures, the materials are exhibiting the special property of superconductivity. So with this phenomena, we just say that this is about the BCS theory, right? So now as we move forward uh, in our next topic, we'll just go to the next topic. So I think that you got a clear idea regarding what is actually BCS has done. So BCS has explained us, right? Bardeen Cooper Schiffer has explained us the phenomena of superconductivity and how this electron and electron are interacting with respect to the lattice vibrations, and we just say that is called as phonon. The electron is getting attracted, and these attractive force which is existing due to this phonon is very much dominant, and with respect to the repulsive force which is existing between these two electrons, and we just they call that this particular pair of electron in which there will be an interaction, indirect interaction will be there. They told us that it is actually the Cooper pair. Now with this we just move forward to the next topic, that is actually the high temperature superconductors. So if you can remember this, just now we discussed about the low temperature superconductivity. Now they have given us the concept of high temperature. So low temperature superconductivity, you require a special temperature, a very less temperature. Now scientists are working here to make the superconductors at the room temperature by applying different amount of what you can say pressure, and a different experiment is actually going on in regard to the achievement of the superconductivity at room temperature. So since when I talk about low temperature superconductivity, we am talking about in terms of Kelvin. 4.2 Kelvin is very, very small. So that is the reason that they are actually moving towards the high temperature superconductor. And these high temperature superconductor, once it has been achieved, that they can be we can just get this superconductivity at a normal temperature, at the room temperature, then definitely it will be a great achievement because of its rapid applications, right, which we have seen in the last class. Now the superconductors, as I told you, here superconductor are having less temperature, that is in terms of Kelvin, 4.2 Kelvin. So here if the temperature is in and around when we talk about the temperature, now what is actually the meaning of high temperature superconductor? If the temperature is greater than 10 Kelvin, right? If the temperature is greater than 10 Kelvin, then such materials which are exhibiting superconductivity at the temperature greater than 10 Kelvin, right? The temperature which is greater than 10 Kelvin, we just call these superconductors are termed to be high temperature superconductors. High temperature superconductors. So the materials which are having the what you can say the temperature which is greater than the 10 Kelvin, we just call that as high temperature superconducting materials. So the materials which are exhibiting this temperature, so we just call that as high temperature superconductors, right? So the temperature, if it is greater than 10 Kelvin, like, so we just they are classified as ceramics. Now, what are the examples of these superconductors? Which materials are exhibiting? Example, you can just take of the ceramics, right? And aluminum oxide, etc. Right? So ceramics is one of the very, very what you can say in the point of applications. We are having a different usage of ceramics in the industry purpose and also in the in day-to-day activity. So we use ceramics, right? So to the large extent, right? So the generally high temperature superconductors are you can just say anisotropic materials, and new oxide superconductors have been discovered when I talk about the aluminum oxides and different oxide. And here the temperature here they talked about the temperature which is having temperature greater than the 90 Kelvin also. They have been discovering this particular materials which are exhibiting 90 Kelvin temperature, so that materials are said to be superconductors. Now these superconducting materials here liquid, you can just say that this superconductivity of 90 Kelvin temperature of material which are exhibiting superconductivity, which is one of the important phenomena of the superconductivity. The liquid nitrogen is coming into picture here. So because of this what you can say, different technological application of these materials. They are highly appreciable, which has been realized that the rate of oxygen is essential for high transition temperature. Here we talk about the oxide temperatures and the different materials which are exhibiting the superconductivity, high temperature superconductivity. So this particular thing is very, very important nowadays. The researchers are actually going on regarding this high temperature superconductors. So in just future, we can just say that high temperature superconductors will definitely come into picture at the room temperature without having various applications, right? So with this, we just start our what you can say today's uh, topic of the uh, when we just start of the low temperature and the high temperature superconductor differentiations. You can just we can have in the examination, he may ask you differentiate between the low temperature superconductors and the high temperature superconductors. You could just make a uh, what you can say different differences. We can make a note of the different differences of the high temperature superconductors and the low temperature superconductor. It may ask in the examination, right? So now we just go for one or two numericals which are very, very important for the examination point of view also. And we just discuss in today's class about some numericals regarding the critical field, right? So the first one that we deal here is the the first one just we are dealing with the superconducting transition temperature. In the examination will give this, but they may give this particular problem also. So the superconducting transition temperature. So the superconducting transition temperature, superconducting transition temperature, transition temperature of lead. So we just take the example of the material lead, right? Of lead is 7.2 Kelvin, right? Is 7.2 Kelvin. So he will ask you now the initial field. Let's see the initial field. The initial field. The initial field. The initial field at 0 Kelvin is at 0 Kelvin. At 0 Kelvin is the value of the critical field we are talking about. So the field is 64 into 10 power of 3. 64 into 10 to the power of 3 ampere right, per meter. Ampere per meter. Like this type of question will be given. Then the critical field at 5 Kelvin. We need to calculate the critical field at the calculate. He will ask you to calculate the calculate critical field field at 5 Kelvin. At 5 Kelvin. So this will be the question in the examination. So what is given in this? First of all, you need to again just read this question. The superconducting transition of lead is found to be the superconducting transition temperature. It means is found to be a lead is 7.2 Kelvin. The initial magnetic critical field of at 0 Kelvin is 64 into 10 power of 3 ampere per meter. He will ask you calculate the critical field at 5 Kelvin. So for this instant, how we need to calculate? First of all, we need to write the what is given actually, right? So here H naught is given. So you can just see at 0 Kelvin, he asked us. So H naught is termed to be how much? 64 into 10 to the power of 3. What is given? You need to write first in the numerical. So into 10 power of 3 ampere per meter, right? And what is given again? It is given, right? What is the temperature? TC, right? Here, here TC is given how much? It is given to be 7.26 for the, see, the initial feed at 0 Kelvin is, see, the superposition transition. So transition temperature is a critical temperature. So the critical temperature value is given by 7.2 Kelvin. So 7.2 Kelvin as it is, we are writing. Now, T is also given, the normal temperature at which we need to calculate the, what you can say, the value of the critical value of the field, right? So 5 Kelvin is given. What is we need to calculate? We need to calculate this actually H value. So how we need to calculate this H value? What is the formula? The formula here is given by H is equal to H naught, the formula that we actually use, right? When you just see the last class, you can understand the what is this actually? 1 minus T by Tc, right? This is in the complete brackets. This will be square, right? So now what we are actually doing here is we just calculate this H value. You can just take these calculators where you can just substitute very simple numericals here. What is there? 64 into 10 to the power of 3. As it is, you need to write 1 minus T. T is what here? Just you can just see this. What is T? T is 5 divided by 7.2. See, divided by 7.2. They are in the brackets. You can just make a square, right? So now, what you will get when you just substitute here, you'll get this particular value, 33, right? You'll get this, right? You'll get this value as 33.64 into 10 power of 3, 33. When just you can just do with the calculator this value, 33.64 into 10 to power of 3, 10 to the power of 3 ampere per meter. This is what the we will get a very simple numericals, right? Ampere per meter. So now we just started today's numerical. The superconducting transition of lead is found to be 7.2 Kelvin. The initial field at 0 Kelvin is 64 in 10 power of 3 ampere per meter. Then he will ask you calculate the critical field at 5 Kelvin. So what is given first you need to write. So since it's a transition temperature, you can just see the first sentence, the superconducting transition of lead is found to be 7.2 Kelvin. So that is the reason that I have written T suffix C is equal to 7.2 Kelvin. H naught is given 64 into 10 power of 3 ampere per meter. T is what? 5 Kelvin. And we need to calculate the, calculate the critical field at 5 Kelvin. So T, he is written as 5 Kelvin, and H we need to calculate. So what is the formula related to H naught, TC, T and H? So H is equal to H naught into 1 minus T by TC whole square. So H is equal to 64 in 10 power of 3 into 1 minus 5 by 7.2 whole square. Now H is equal to 33.64 in 10 power of 3 ampere per meter. So now this is what you'll get. In the same instant, he will ask you the different question. He may ask you the question of, right? See. Yeah, I think that you got a clear idea. So the other question that he will ask you in the examination, the second numericals that we'll deal with the here, the critical, see, the critical temperature for mercury, the critical temperature, the critical temperature for mercury, the critical temperature for mercury with isotopic mass. Now this is different, right? with isotopic mass, with isotopic mass, isotopic mass, right? Isotopic mass is 4.185 Kelvin. Isotopic mass with 4.185, right? 185 Kelvin, right? So calculate its critical temperature. Calculate, he will ask you, right? Calculate its critical temperature. Calculate its critical temperature. Calculate its critical temperature. Calculate its critical temperature. Temperature, right? When its isotopic mass is, when its isotopic mass is 203.4, right? With 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 isotopic mass, with isotopic mass, with isotopic mass of 203, 203.4, 203.4, right? 203.4, right? So what is given here first of all? So here you need to know the relationship between the critical temperature and the isotopic mass. So here, first of all, the relationship between this temperature is found to be 1 by root m. This is very, very important. So what it means here, we can just write this TC1, right? See, TC1 by TC2 is equal to root of m1, right? Or else you can just what you can say using this, right? Uh, okay. Now we just see, we can just write this m to the power of, see, TC1 by TC2, which is given by uh, root m, right? 1 by root m, right? I just told you that is 1 by root m. So what it will be, m1 by m2 whole to the power of, inversely proportional, right? So minus 1 by 2. Now this relation you need to understand. Just for that instant, we can just write this as we need to calculate this value of TC. So what is TC2? See, you can just see we need to calculate TC1. So TC2 value is 4.185 Kelvin. So M1 is given as, here you can just see, M1 is given as 199.5, right? It is given, right? It is given now. Isotopic mass of 199.5, right? Mass of 199.5 here. So 199.5, M1 is given. And what is M2 here? So M2 is given to be 203, 203.4. So you just substitute here, you'll get the value of TC1. So TC1 is equal to 4.185, right? Divided by into what is that? 199.5 by 203.4 whole to the power of minus 1 by 2. So you'll get this value of TC1, which is equal to 4.145 Kelvin, right? So now the critical temperature for mercury with isotopic mass of 99.5 with 4.185 Kelvin that is a temperature, calculates critical temperature with the isotopic mass of 203.4. So we should know the relationship between the critical temperature and the isotopic mass. So Tc is inversely proportional to 1 by root m. Tc1 by Tc2 is equal to m1 by m2 whole to the power of minus 1 by 2. So we just substitute this in the relevant formula and we'll obtain this value. So with this, I think that you are very much clear about the numericals which may ask you in the examination. Thank you, everyone. We'll meet again in the next class.